All right, here's another optimization problem. This is one that I call the box problem, maximizing volume. Now, I've seen a bunch of different versions of this, but this is sort of the basic starting version of this problem. Once you understand how to do this basic box problem, then you can do the more complicated ones that come up sometimes. But here's the idea. You've got you want to make a rectangular box that has no top, and you're making it out of a 24-inch by 36-inch rectangular piece of cardboard. And what you're going to do is you're going to cut equal squares from each of the corners, and then you're going to bend up the sides. Here's what I mean. Let's say that this is our piece of cardboard, 24 by 36 inches, right? And if we cut a square out of this corner here, and then cut a square, an equal square, just like this one, cut another square equal size out of this corner, and then the same size square out of this corner, and then the same size square out of this corner. So if we cut a square out of each corner, what we're going to have is, we're going to have a piece of cardboard that now looks like this. And then what we can do is, along this line, we can fold this up. Along this dashed line, we can fold this up. Along this dashed line, we can fold it up. And then along this dashed line, we can fold it up. So we would fold up the four sides, and then you can put tape at the corners, and you'll now have a box. Okay? Very basic way to make a box. And so what we want to do is it says find the dimensions and volume of the box, of that box that has maximum volume. And the idea is if you make the squares too small, you'll have a very flat box, but it'll have a lot of ground area, but it won't have very much volume because the sides aren't very high. But if you cut the squares really large, they'll have really long sides, so it'll be very deep, but the inside will be very thin. So somewhere between there is a box that has the highest volume possible. Okay? And so this is a maximization problem. In fact, it even says maximum volume. So when we look at this, when we look at identify a formula for what is being maximized, well, we're maximizing volume. Well, there's lots of different volumes. There's the volume of a sphere, there's the volume of a cone, the volume of a cylinder, the volume of a rectangular prism, the volume of a triangular prism. There's lots of different things that we could have the volume of. So we got to try and figure out what shape is this going to create. Well, it says that it's a rectangular box. And a rectangular box is basically, it's what we call a rectangular prism. And if we're maximizing volume, then we need the formula for the volume of a rectangular prism. And that's a really easy one. So our formula here is going to be volume is equal to length times width times height. Okay? So we've got our formula, but now we have a problem because we have 1, 2, 3 input variables. And we need to have only one input variable. And that means that we're going to need two separate equations that allow us to be able to take out two of these variables. And those two separate equations have to relate one of these variables to one of the other variables. And then the other equation has to relate one variable to the other variable. So we got to try and looking at this diagram, or we got to try and come up with a way that these variables are related to each other. Well, here's how it goes. The idea is that when you cut out these corners and fold up the sides, that the dimension of this square winds up being the height of the box. Because look, when you take this little flap here and fold it up, that flap becomes how tall the box is. And this flap is the same height, and this flap is the same height, and this flap is the same height. So what winds up happening is that all these dimensions on the square are equal to the height of the box. Height We also know that this overall piece of cardboard that we're using is 36 inches long from top to bottom, and it's 24 inches wide from one side to the other. Okay? And then, if you'll notice something, after you cut out these squares, right, the distance from here to here, that distance right there, that is the width of the box. And then after you cut the square out, you're going to have this part from here to here. That is the length of the box. And here's what I want to show you, is that the overall distance from here to here is 36. But if we cut out one H and then a second H, what will remain from here to here is the length of the box. So what I'm showing you is that length is equal to 36, the full distance, minus H minus H. So length is equal to 36 minus H, or minus 2H. And the width of the box, it's the same thing. The width is from here to here, but the distance from here all the way over to here, that's 24. And if we cut out H here and then cut out H here, the height is being cut out. What we have left between is the width. And so the width is equal to 24 minus 2 H's. So the width is equal to 24 minus 2H. And so now look, with these two equations, we have now related the length to the height and the width to the height. So we can now do step 2, which says substitute expressions for variables so that you have a single input variable. And so if I put this 24 minus 2H in for width and put in this 36 minus 2H in for length, we will have one output variable and one input variable, H. So our formula now is going to become volume is equal to, well, what's length equal to? 36 minus 2H. 36 minus 2H. What's width equal to? 24 minus 2H. And then for height, we'll just put the H. And this is now our volume formula as a function of height. Okay? And so now we can look at step 3. It says identify the interval of input values if relevant. Well, it is relevant here. Height cannot be a negative value. Geometric distances cannot be negative. In geometry, in the world of space, all distances are positive, or they are 0, which means there is no distance. So height can only be as small as 0. So for step 3, we're going to say that the smallest value that h can be is 0. And then, similarly, length and width, the shortest they can be is 0. So if we look at these two, this 36 minus 2h and this 24 minus 2h, okay, those cannot be smaller than 0. Now, length would be 0 if h was equal to 18, because 2 times 18 is 36, and 36 minus 36 is 0. So by the length, h can equal 18. But look at over here at width. Width will equal 0 if h is 12, because 2 times 12 is 24, and 24 minus 24 is 0. So logically, the longest that h can possibly be is 12. So we're going to put a 12 right here. So h has to be somewhere between 0 and 12. So it has endpoints. It has an interval. Okay? All right, so now we'll go to step 4 and it says optimize the function using the procedure from optimization 1. Now, we could distribute this and turn it into a polynomial and then optimize it. In fact, well, I guess we can go ahead and do that. Let's distribute the h here, and this would become, we'll bring over the 36 minus 2h. And now I'm going to distribute this h here, and I'll have 24h minus 2h squared. Now I need to distribute this binomial with this binomial. And so what I'm going to do is I'm going to do 36 times 24h. I'm going to need a calculator for this. 36 times 24 is 864h. 864h. Then I'm going to do 36 times negative 2h squared. So 36 times negative 2 is negative 72h squared. Now I'm going to do this negative 2h times 24h. That's going to be minus 48h squared. And then lastly, I'm going to do this negative 2h times negative 2h squared. And that's going to give me plus 4h to the third power. Now I'm going to rearrange this, because I would like this to be in standard form where I have the highest power down to the lowest power. So 4h cubed, and then minus 72h squared and minus 48h squared, so that's negative 72 minus 48. That's going to give me negative 120, negative 120h squared, and then plus 864h. Now this can be simplified because it looks like all these values can be divided by 4. 128 divided by 4. Because remember, I'm setting, well actually I'm sorry, I'm not at the derivative. I'm going to wait to do that. I'm not going to divide it by 4 yet. Hang on. Let's do the derivative first. So now v prime is going to be equal to 12h squared minus 256h plus 864, and we're going to set that equal to 0. Now to find these zeros, we can use the quadratic formula. We can also simplify. I decided I'm not going to simplify it. Or we can use a graphing calculator. I'm going to go get a graphing calculator. A TI-84 here, and I'm going to enter this in y equals. I'm going to put the derivative in. I'm trying to find out what the zeros are of the derivative. So I'm going to key in 12h, well it's x squared in the TI-84, minus 256x plus 864. Now I'm going to hit graph. We'll see what it looks like here. All right, there we go. There's 1, 0. We only got 1, 0. There's got to be another one somewhere. Let's find out where it is. I'm gonna kind of zoom out. Zoom out. Let's see if when I zoom out, do I see the other one? There's one. There's 2 of them. There they are. All right. So watch what I'm going to do now. Well, you know what? I'm just going to find them. Well, here, watch this. I can hit zoom, and then I can select box, or I can zoom in. Watch what I do when I zoom in. If I put the cursor, where's the cursor? There it is. You see the cursor right there? If I put it halfway between the 2 and then zoom in right there, now it should show me. There's one, and there's the other. Okay, good. All right, now, if I move over here, I can see, look, this other 0 all the way over here, I don't know if you can see this, but it says x is equal to 16.17. So I know that that one right there, that 0, whoops, I know that that second 0 right there is actually larger than 12. And because it's larger than 12, I'm not even going to look at it. Okay? I'm not even going to look at it because our interval runs from 0 to 12. So I'm not going to look for that one. But let's see where this one is over here. Let's see where this 0 is. If I move the cursor near here over here, find out what the x value is right there. All right, what's the x value right about there? Looks like it's about 4.4. So we're going to search between maybe 3 and 6. So now I'm going to hit second, trace, get the calculate menu, choose option 2, 0. Left bound, I guess I'll go with 3, enter. Right bound, I'll go with 6, enter, and press enter. And it says that I got a 0 at 4.2031. 4.2031. X equals, now I got to make my, I'm going to make my table, right? Because I'm doing an optimization. So H equals, and then volume equals. My endpoints are 0 and 12, right? So now I'm going to put the, there's only one critical value on this interval for this, for my original function. and it's at 4.2031. 4.2031. And now I need to plug these values into the original function. I can either plug it in here, or I can plug it in right here. And I'm going to go ahead and plug it into this factored form of it. I know that if I put the 0 in, the whole thing's going to become 0. Because if this is 0, 0 times this is 0, times this is 0. So I know when I plug in 0, my volume's going to be 0. Similarly, when I plug in this 12, 12 times 2 is 24, and 24 minus 24 is 0. And when this is 0, times this is 0, times this is 0. So I know when I plug in 12, I'll get 0. Now let's see what happens when I plug in 4.2031. So I'll key in parenthesis 36 minus 2 times 4.2031, close parenthesis, open parenthesis, 24 minus 2 times 4.2031, close, times 4.2031, press enter, and I get 1,808.5611. 1,808.5611. And that is the volume. That is the maximum volume. And the question says, find the dimensions and the volume. Well, we just found the volume. The volume of the box of maximum volume is 1,808.5611 cubic, or is this inches? Yeah, this is in inches. This is 24 inches and 36 inches. So that's inches cubed. That's our answer for the volume. Now we need the dimensions. We already know what the height is. The height is 4.2031 inches. So height is 4.2031 inches. Okay? Now we need the width and we need the length, because there's 3 dimensions. It's length times width times height. And what we'll use is these 2 formulas right here. Length is equal to 36 minus 2 times h. So 36 minus 2 times, and h is 4.2031. 4.2031. So our height is 27, or excuse me, length. I'm sorry, our length is 27.5938 inches. And now we'll do the same thing for width. It's 24 minus 2h. 24 minus 2 times 4.2031. And that's 15.5938. 15.5938 inches. And so we have identified this box. If you make the box with those dimensions, which I realize are very precise, but if you make the box with those dimensions, you will get the most volume that you can possibly get out of a box made from this piece of cardboard. Now, if you make it with a larger piece of cardboard, if you make it a 48 by 36 inch piece of cardboard, then you'll be able to make a larger box, okay? But this is the box problem when you want to maximize volume. If this was a little bit of a whirlwind, this problem, what I recommend that you do is watch this video again. Watch it again. Go back through this problem. Make sure you write down everything that I wrote down. If you do it maybe, what if you did it once a day for 4 days? Eventually, this would become very familiar to you, and then when you started seeing other problems that were like it, you wouldn't have any problem at all solving this, okay? But this is what I call the box problem, and then maybe you'll face another problem that's the box problem, but maybe it's a little more complicated. You might face a problem where you take a piece of cardboard and you cut corners out of it, but you're also going to fold over a lid. I've seen that one before too. So there's a lot of interesting variations to this. But it's the box problem. Hopefully you're getting better at optimization. Good luck.